we covered everything related to rectangular cross section for single reinforced section and double reinforced section. Last time we started a little bit new topic called T section, which is common in our building because we have concrete slab. This concrete slab will work with the beam as one unit. So we have flange and web. This part called web. And part of your slab will work as flange. Not the whole width of your slab will work, only effective width. So if your beam is intermediate beam, we have a certain width of the slab will work together with your web as T section. Based on ACI specification, to calculate the effective width or B flange, sometimes you can call it B effective or B flange, that's fine. We have three values. We will use the smallest one. 1/4 of your span length. This beam has span length. Quarter this span can give you the first value. Second one, 16 H flange. Slab thickness called H flange. 16 H flange plus B web, this width, or center line to center line. What you mean? Between this beam and this beam, we have a center line here. Between this beam and this beam, we have a center line here. This distance can be one of them. So you calculated three values, use the smallest one. If your beam is intermediate beam, like this, we have flange from this side and flange from the other side. Sometimes your beam called edge beam at the edge of your building. So we have only one slab or slab from one side, nothing from the other side. So in this case, we have different values for your B effective. Your B flange will be something like this. And your cross section, not T section, but L section, looks like this. Anyway, 1/12 of the beam span, L divide 12, or your web width plus 6, your H flange, or between this beam and this beam, we have a center line here, this distance of your center line. Which one is the smallest value? You can figure out what is the B flange of your L section. Any question? Last time we started with the first case. Anybody remember what was the first case?
Where the neutral axis.
Yeah. The story that we learned from the beginning of this course. What was the story? We have a cross section. We have in one side steel reinforcement. That means we have tension. On the other side, we have compression. In between, we have something called neutral axis. Sometimes it doesn't matter if your cross section is rectangular cross section. I don't care where is your neutral axis, here or here or here. Why? Because if your cross section, your neutral axis is here, this part is rectangle. If your neutral axis is here, this part still rectangle. If your neutral axis is here, this part still rectangle. But if your cross section is a T section, big difference between your neutral axis is here because this part is a big rectangle. That's fine, but it's rectangle. But if your neutral axis is here, your shape of the cross section above your neutral axis change. We have something like this. It's not rectangle, something else. So, big difference between your neutral axis in flange or neutral axis below your flange. First case, we will assume your neutral axis in flange. So, we have compressive stress block at this location, and we can be converted to equivalent compressive force C, and we have tensile force T in your steel reinforcement. Your T will not change, equal area steel time F yield. Your compressive force C will not change, only one change. 0.85 FC prime A time B flange or B effective. In rectangular section, this width is the same like this width. But in T section, this width not the same like this one. So we are using B effective or B flange. Both of them are equal. The only unknown is your distance A. I can figure out what is the distance A. A equal beta 1 times C. I can figure out what is the distance C, your neutral axis depth. This neutral axis depth C must be smaller than or equal H flange. To say my assumption is correct, you assumed your neutral axis within the flange and your neutral axis depth smaller than total thickness of the slab, then your assumption is correct. Go ahead and get your nominal moment. Take moment here, maybe. Your nominal moment will be T times D minus A divided 2, area steel F yield times your distance. If you would like to get your design, you need to multiply it by phi. Phi equal 0.9 most of the time, 0.9, or based on what is the value of epsilon T. Anyway, this is your design bending strength. And we solved one example last time. But what will happen if your neutral axis not within the flange? Let's start first with this example. I would like to try something first. Your T section, we have effective width is given 30 inch. We don't need to calculate what is the value of B flange. It's given. Your H flange equal 4 inch. Your depth D equal 30 inch. Your area steel equal 10.12. Everything is ready. First step to solve your T section, we need to assume, and we would like, your assumption is correct. I would like, we will assume your neutral axis within your flange. So please say, assume neutral axis within the flange. It's an assumption, and I will do my calculation based on this assumption, and I will check if my assumption is correct or not. Then we have stress block here, compressive stress block, 0.85 F prime C, with depth A. I forget. This distance or this depth equal C, small c, for your neutral axis. Anyway, and we have equivalent compressive force here, capital C. In your tensile tension reinforcement, we have tensile force T. That's right? Any questions so far? Your C equal T. Very similar to a rectangular section. So 0.85 F times C, A times B flange equal area steel times F yield. Put your number, 0.85 F prime C 4000 times A times B flange 30 inch equal area steel 12.12, 10.12 times F yield 60,000. What is the value of distance B?
$5.95.
5.5
$95.
inch. Okay, your distance A equal beta 1 times C. Your A 5.95, beta 1.85. Can you tell me what is the value of C? Something maybe higher than 6 inch. 7 inch. Wow. Your distance or your depth of your neutral axis C equals 7 inch, which is greater than your H flange, which is 4 inch. That means your neutral axis is not within the flange. Your assumption is not correct. So to solve your T section, we need first to assume your neutral axis within the flange. Do your calculation, check what is the depth of your neutral axis. Your depth greater than the depth of your or the thickness of your flange, then your assumption is not correct. Your neutral axis outside the flange.
Dr. Raymond?
Yeah.
What if your A is in the flange but your C is not?
No, my concern is A. That's right. My concern is A, because where is your stress block? This is the most important one. This one must be within. But if your A equal maybe 3 point or maybe 4 inch, your C will be 4.5, for example. So I think you still can say I can use this flange and my calculation will be correct. Okay? So your neutral axis outside the compression flange. You are right, Elmar. We cannot say neutral axis, but the specification make a relation between the location of your neutral axis and concrete flange. Anyway, so your assumption not correct. We need to repeat our calculation based on the new location of your neutral axis. What will be the new calculation? We did something like this before. Do you remember? If we have double reinforced section, we have two options. Do you remember? No? Yeah, assume your steel here is yielded. and do your calculation and check if this steel yielded or not. If not, we need to repeat. If yes, that's okay, keep going. Anyway, so we need to do another calculation that your neutral axis within the web. So right now, your part of cross section under compression, something looks like this shape, and your steel reinforcement at the bottom. So your cross section will be divided into two parts. First part, second part. First part and second part. First part of your area steel called area steel flange, and this area and this area. Second part will be another part of your area steel, which called area steel web, with the remaining part of your area under compression. Remember, this area steel web plus area steel flange equal area steel. This shape plus this shape equal the total shape of area under compression. Any question so far? Any question? One more time. Right now, my neutral axis outside your flange. So the area under compression above your neutral axis looks like T section. And we still have area steel. We would like to divide this cross section to two parts. First part of your area steel will work with these shapes of flange.